Today we're diving into a cosmic mystery, one that had some of the greatest minds in physics totally stumped. And we're going to talk about the brilliant, unsung mathematician who figured it all out, revealing that our universe, well, it might just be a little bit leaky.
Okay, picture this. You're floating out in the blackness of deep space. You throw a rock. Basic physics, right? Newton's laws say that rock should just keep going forever. But what if I told you that eventually it slows down and stops? Now, this isn't just a weird thought experiment. It points to a really deep, kind of unsettling question about the universe itself. Where did all that energy just go?
And this isn't just a thought experiment. No, this points to a real cosmic paradox. You see, about a century ago, this whole problem of energy conservation wasn't just a puzzle, it was a full-blown crisis that had even Albert Einstein scratching his head while he was building his masterpiece.
So, you might think Einstein would have the answer, right? Well, nope. The solution didn't come from the big, established names in the field. It came from an outsider, an unpaid mathematician who saw something that absolutely everyone else had missed. And her work? It wouldn't just solve Einstein's problem, it would fundamentally change how we see reality itself.
To really get what happened, we need to rewind the clock to 1915 at the University of Göttingen in Germany. Einstein's there, he's presenting his brand new theory of gravity, and without even knowing it, he's also presenting a massive, massive problem that came along with it.
So here was the huge issue. General relativity was a game changer, right? It described gravity not as a force, but as the actual curvature of space-time. But inside this incredible new framework, the math just didn't add up. The total energy in a system didn't seem to be conserved, which violates one of the most sacred rules in all of physics. I mean, where was the energy of the gravitational field itself going?
So you've got Einstein totally wrestling with this. And he's not alone. The legendary mathematician David Hilbert jumps in, and even he gets stumped. Now, Hilbert did manage to find a partial solution, a set of equations called the Bianchi identities that seemed to work. But here's the catch. They only worked for a completely empty universe. You know, a universe with nothing in it. For a universe like ours, packed with stars and galaxies, they were useless. Both of these giants had hit a wall.
But lucky for, well, all of physics, Hilbert knew exactly who to call. He had a new assistant, someone whose unique area of expertise was perfectly suited to untangle this cosmic knot, a woman named Emmy Noether.
Emmy Noether was an absolute force of nature. She wanted to be a mathematician just like her father, but she was denied official admission to her local university, simply because she was a woman. The university senate actually said her admission would overthrow all academic order. Can you believe that? But she didn't let that stop her. She kept pushing, and eventually became only the second woman in all of Germany to get a PhD in mathematics.
So what was her secret weapon? It was a field called symmetry. Now, we all kind of know what symmetry is, but in math and physics, it has a very specific meaning. It's any action you can perform on a system that leaves it looking exactly the same as when you started.
For example, take an equilateral triangle. You can spin it by 120 degrees or 240 degrees, and it looks identical. That's what's called a discrete symmetry. There's a specific number of things you can do. But where Noether was a real genius was in something way more abstract. Continuous symmetries. Imagine a perfectly straight infinite line. You can slide along it by any amount, a tiny bit, a huge amount, and it still looks like the same infinite line. That is a continuous symmetry. And believe it or not, it's the key to this whole story. And this is it. This is the moment where everything changes. Noether took her deep, deep understanding of these abstract symmetries and pointed it right at Einstein's problem. And she didn't just solve it. She created an entirely new foundation for physics. She looked at this whole thing and asked a question so radical it turned physics on its head. For centuries, everyone just assumed that laws like the conservation of energy were fundamental, bedrock rules of the universe. But Noether wondered, what if they aren't rules at all? What if they're just the direct mathematical consequence of symmetries that are already built into the fabric of the universe? And this is the absolute beauty of her first theorem. She proved with pure mathematical certainty that for every continuous symmetry you find in the laws of physics, a conservation law pops out. It's incredible. If the laws are the same no matter where you are in space, boom, you get conservation of momentum. If they're the same no matter which direction you're facing, you get conservation of angular momentum. And here's the big one. If the laws of physics are the same at all times, you get conservation of energy.
So, you might be wondering,
How on earth does that work? Well, without getting tangled up in the hardcore math, the logic is just elegant. It starts with a simple idea. An experiment will give you the same result whether you do it today or tomorrow. That's time symmetry. Noether showed how this symmetry forces a specific thing in the equations of motion to always stay constant. And when you figure out what that constant thing is, you find out it's exactly what we've always called total energy.
Okay, so let's bring it all back to that rock we threw at the beginning. How does this amazing insight solve our original paradox? Why does that rock in deep space eventually just stop? Well, the answer is just as mind-bending as the theorem itself.
Because here's the mind-bending twist. On a grand, cosmic scale, our universe does not have time symmetry. It's expanding. In fact, that expansion is accelerating. The universe was a totally different place 13 billion years ago. It was hotter, denser, and it's going to be a very different place billions of years from now. So the stage on which the laws of physics play out is not constant through time.
So why does energy seem to be perfectly conserved in every experiment we do here on Earth? Well, it's because on our human timescales, days, years, even a few centuries, the universe's expansion is so tiny it's basically zero. So for us, time symmetry holds, and energy is conserved. But stretch that out over millions or billions of years, and the expansion becomes huge. The symmetry is clearly broken. And if there's no time symmetry, there's no law of energy conservation.
And there you have it. The paradox is solved. As that rock travels through space for an unimaginable amount of time, the universe literally expands around it. And since there's no cosmic time symmetry, there's no cosmic law of energy conservation for it to obey. The rock's energy doesn't go somewhere else. It doesn't turn into something else. It just vanishes.
But wait, there's more. As if that wasn't enough, Noether wasn't done. Her second theorem explained how this all fits into general relativity. See, energy is conserved locally, in little patches of spacetime. But because spacetime itself is curved and stretching, energy can kind of leak out between those patches. Imagine a long water pipe made of many small sections. The water inside each section is conserved, but if there are tiny cracks at the connections, you can lose some water along the way.
So you see, this wasn't just about fixing one little problem in Einstein's theory. What Emmy Noether did was provide a completely new way of thinking about the universe, a new foundation for basically all of modern physics.
But the story takes a really tragic turn here. Just as she was revolutionizing physics, her own world turned against her. After years of working for free, she finally got a paid professorship. But then in 1933, she was dismissed by the Nazis because she was Jewish. But she never stopped working. She literally taught students from her own kitchen before managing to escape to the United States, where she taught until her sudden death just 2 years later.
And the one person who truly understood the scale of her genius, well, that was Albert Einstein himself, the very man whose problems she had solved. In her obituary, he wrote this incredibly powerful tribute, calling her the most significant, creative, mathematical genius to emerge since women had even been allowed to get a higher education.
And my goodness, was he right. Her theorems weren't just a footnote, they became the actual bedrock of 20th century physics. They're absolutely essential for understanding quantum mechanics, for the discovery of fundamental particles like quarks and the Higgs boson, and for explaining everything from why electric charge is conserved to the nature of the fundamental forces themselves.
In the end, Emmy Noether taught us something profound. She taught us to look beyond the laws themselves and search for the deeper patterns, the symmetries that give rise to them. And it leaves you with this amazing final thought. If our most fundamental physical laws are really just shadows cast by the universe's symmetries, what other incredible truths are out there, hiding in plain sight, just waiting for us to finally see the pattern?